I am live, but I'm currently muting Xenotime because he's getting some stuff set up. Hi! Okay, OBS did not crash. Sweeting at Sing, it's me, Z. Hello, everybody! Oh my god, my voice is a little out of it today. Hello, I hope you can hear everything, hear me just fine. I hope all is going well. Let's just do a quick attendance. Hello Eggy, hello Cillian, hello Millennium, so glad you're able to catch the stream. Hello Astral Tropos, hello Stella Curie, hello Warpy, hello Eggy, hello Nikki, hello Aegis, hello Shub, hello Architelos, hello Yukikaze, hello Pembu, hello Pizza Man, hello everybody. Aegis, I love your profile picture. Recently I've been obsessed with Kirby, actually. I've been playing a lot of Kirby games, and I've been playing, oh, I'm forgetting what it's called, but it's on Switch. I'm borrowing a friend's Switch to play, it's like 2D Kirby, and I really want the one where you can, like, explore the worlds. So, I really like that profile picture. It's adorable. Hello, everybody! I hope everybody is having a splendid afternoon. My voice is a little dead today for some reason. I'm not sure why. So I'm drinking a little bit of coffee, but this collab has been much in the works. I am so excited to share this with you guys because this is really the perfect combination between both me and Xenotime's passions. For me, it's physics, astrophysics, and for Xenotime, it's chemistry and also maybe a bit of physics. So, woohoo! We're here and we're ready to get started. Hello, Eternal. A sweet and nice future said she might not come back. This is so sad. Yeah, no, I assume you're talking about Gura's announcement a few weeks ago, a week ago or so. It's very, very unfortunate what happened. But hoping that I'm gonna keep watching the streams and things will be good. Hello, Doc. Hello, Salt. Alright. I am curious to hear what you guys have been consuming recently, because I have been drinking a lot of coffee, and last night I had a delicious chocolate pie. I'm not usually a huge fan of chocolate pie, but this one was actually quite good. And today I'm gonna get some ramen, so I'm really, really excited. I mean, what is chemistry if not physics under very restricted conditions? Well, I'd say that physics is basically every field, right? I think at its core, physics is everywhere. So, yeah, exactly. Chemistry is physics. Physics 1. Orbeez, when Xenotime comes in, we gotta say that physics won the live stream. Can't drink coffee? What? How do you even exist? No. Also, Escilla, I'm not sure if I know who that is, but I'm happy to check out their channel. That's really unfortunate. Ramen is god. Yeah, no, ramen is so good. I feel like I crave ramen very, very often. Everything is physics. That's why it's the best science. Exactly. What is physics if not math? Okay, at least I'm not collaborating with a math VTuber, right? If that was the case, we would be having a very different argument. Oh. Well, tomorrow is going to be my 2,000 sub celebration milestone live stream. If I'd be honest, I'm still deciding on when is a good time. Things have been really, really crazy for me IRL, and I'm wondering if there would even what the best time would be. Currently, I'm leaning towards 1 p.m. Pacific time, which would probably be it would probably be good depending on what time zone you're in. I'm also considering maybe moving this to next weekend, but I have a feeling I'll be much more busier next weekend, so yeah. Everything is physics, that's why it's best science, yeah. Can't drink coffee, so I get by using willpower. Wow, that's incredible. Random 1-minute naps. Random 1-minute naps. Or 20-minute power naps are the move. Though, I heard that 30 minutes might actually be the ideal time. It has to do something with REM sleep. Maybe this is my next collab with Faye. Learn, because she's a doctor. She can help me understand what the sleep schedule will be. What is math if not philosophy? No! No! Orbeez, no! Physics is at the top of the food chain, I promise. It was 20 minutes or 1.5 hours. Oh, I see. Yeah, no, I need to learn how to nap better. I usually do 20 minutes. I don't really like coffee. I make do with tea and Sprite. Ooh. I feel like I've been trying to... Oh, here. Sorry, I'm gonna get things set up. I just saw that Xenotime just sent a new link. Just gonna make sure that's working. 30 I think makes you groggy and an hour makes you groggy. It's so weird how that works. 8 hours is a good... Yeah, no, that's my kind of nap. That's my kind of nap. Coffee, tea, and Sprite. Yeah, I've been trying to drink some more caffeinated tea, and also recently I have been drinking a little bit more matcha, but not like the overly sugary-fied matchas from Starbucks or something, but like genuine, real matcha, but without any additives, so it's incredibly bitter. I feel like the caffeine rise for matcha is a lot more slower than what I'd get with anything else, so yeah. So it looks like Xenotime is getting some this is crazy to me. Xenotime's getting some last minute packages for this experiment. So we're gonna be waiting around for just a little bit. It won't take too long. Hey, that's a good idea. 8 hours. 5 hours sleep, gang? No, no, no. I feel like anything less than 8 hours for me, I start to collapse. Yeah. Though, I feel like streaming more also does affect my sleep schedule for some reason. For context, right now, it's around 10 a.m. in Pacific time, and I got up at around 9, which, I mean, that is typically when I wake up. But I remember around last year when I was streaming, I was like getting up at like 7 or 8 to stream. So if anything, I feel like streaming has been affecting my sleep schedule in various ways. How did you survive college needing 8 hours of sleep? Well, I feel like for me, I try to do my best to get a lot of sleep. My strategy actually is to go to the gym, because I realized that if I go to the gym at night, I tend to naturally feel really tired, and then I have no choice but to sleep, and then I tend to get up early. I don't know about you guys, but I'm of the belief that if you stay up really late, then you feel less productive the next day. And for me, I felt like, at first I was also like getting like no sleep and pulling all-nighters, but then I realized that if I want to actually study for longer periods of time, it's more healthy for me to get a good night's sleep. Yeah, 5 hours is awful. 5 hours, I feel like, is the amount of sleep you get if you have like a flight the next day. How's university been lately? Well, as you guys know, I did recently get published, so I think things have been lighter, but you know, the grind never ends. So I'm back on the grind again. Things have been great. There was a lot of like celebration and fun last week. Went out for dinner a few times, got ice cream a few times. I am a sucker for ice cream, by the way. Like, dark chocolate ice cream is the bane of my existence. I think that's the way you use that word, right? I don't know. But yeah, have been back on the grind. If anything, things are ramping up a lot more just because it's approaching the end. Well, nah, not really. It's not really the end of the year, but you know, things have been ramping up. So yeah, I mean, it's been great. How has things been for everybody else in chat? I hope work or school or wherever you are is going well. Speaking of, there is one thing that I did want to cover maybe in the next stream for the 2,000 sub milestone. We actually did a census a while back, and I've been continuously forgetting to actually post like the results for it. So maybe that's something that we go through during the next stream or the stream after that, because there were some really interesting results. Like, you guys come from really different areas. I was wondering if it would be mostly college students or so forth, but it actually seems like there's a really good variety in age, experience with physics, and so forth. Yeah, you'd love to see it? Yeah. Wait, bane of your existence is something you despise? Oh my god. Oh, I'm so bad at using... This is just like last week when we were... What was the phrase it was in the Astrobytes article that was like something about like shot of the gun or whatever, and I just did not understand the metaphor. I almost forgot about the sentence. Yeah, no, I kept forgetting about it too. I have finals in 2 weeks and 2 papers due next week. Oh my god. Yeah, no, best of luck. That sounds really intense. Yeah, I've also noticed just in general that it's... When people are more stressed, like, the vibe of the university tends to change. Yeah, shot in the dark. No, it wasn't shot in the dark. It was like... Oh, what was it? Oh, wait, let me actually pull it up again. It was the bullet cluster article that just came out. Oh, it was like a smoking gun. It was like there's no... It was like there is no smoking gun for... Yeah, there's no smoking gun found in the hunt for dark matter, and I just straight up did not understand what that meant. Hello, Germanium. Hi. We're just waiting a little bit for Xenotime to get some packages for a live experiment, which I'm actually super excited about. Actually, before we got on this, Xenotime was, like, being very secretive about what this experiment might be. But this stream will actually be a really nice combination of both a lecture format and a live experiment. So this will be very, very exciting. In the meantime, let me adjust this. I'm actually curious, do you guys have any good food recommendations? I have some friends that are going to be in town soon, and I mean, I feel like ramen is always a really good choice, but if you have any good recommendations, I feel like I'm down to try something new. Actually, a few days ago, I tried Pakistani food, which was interesting. It was very different from... I've never really had authentic Pakistani food before. It was quite good. The thing that I got was unfortunately really oily, so I didn't really like it, but I think some of my friends, I shared with some of my friends and they had stuff that was like really, really good. Fuzz good? Oh, bulgogi is so good. Yeah, no, I love that. I feel like K-barbecue is a great choice for really big groups. Japanese, Chinese food, yeah. I feel like you can't go wrong with Asian food. Yeah. I recently had a friend from Japan visit, and what I didn't realize is she really wanted to go to like In-N-Out, because I was suggesting like, oh, we could try some really good like pasta and like Italian food, but turns out the pasta in Japan is pretty dang good. And she was like, yeah, I want to go to In-N-Out. What? Like, I feel like that's so weird for me because, like, In-N-Out is just a fast food chain. Oh, Thai food. Oh, that is smart. Wait, let me write that down. That's really creative. I think a good bowl of pad Thai is really good. Filipino food? Jollibee? I've actually never been there either. Thai food for my birthday was okay. Yeah, I'll have to do some research. Thai food? Yeah, I feel like Thai food is actually a really good choice. Maybe I'll go with that. Yeah, no, it's great. Yeah, I feel like Thai food is a good choice. Yeah, thank you for the recommendations. This is great. Yeah. Whoa, my head did a thing. Well, I hope Xenotime is back soon. As an FYI, I do need to head out at exactly 11:30, so in about an hour or so. I have a really important meeting and it takes like 20 minutes to get there, and I'll have to get ready and everything. So it's gonna be a speed run, but if it ends at 11:30, I'll have plenty of time. I want to try Jollibee. I don't know where the nearest one is to me either. Try to make? Oh, wait. I actually haven't cooked in a while, but recently I got a banana bread mix from Trader Joe's. And I'll see if I can try to make it. The issue is I don't have any eggs. And it's been crazy. I went to Trader Joe's and there was a sign that said only 1 egg carton per family. And There were no eggs left. I mean, that being said, I did go in the evening, afternoon, so... Oh, looks like Xenotime is here! Alright, perfect. Alright, let me quickly unmute. Unmute. Alright. Maybe you can try saying something? Hello? Okay, I think it works. Alright, well, I can hear you. Chat, can you hear Xenotime? Alright. I mean, it looks like you're bouncing on my screen.
Okay. That's a good sign.
Alright, we got that, dudes.
Okay. Also, yeah, I will send you another message.
Yeah. Take your time. Oh, the reactive link. Here, let me...
Yeah, in the meantime, I can say what just happened. So,
wait,
because I've been really stupidly busy, on Z-Stream, you're not live yet. Wait. Oh my gosh. Is my microphone somehow muted?
Huh?
Okay, it seems like my stream can't hear me. Whoa. And I don't know why.
You just started to sound deep fried.
Am I still deep fried?
Yeah, a little.
Okay, wait.
Oh my god,
I'm sorry, I brought all this stuff.
My ears!
I forgot to hit the go live button, that's why. I forgot to hit the go live button. I'm not used to stream keys. OBS broke because I changed account. Oh my gosh.
Oh god. Well, the audio's better.
I think... Oh my gosh, I had the whole starting soon thing going the whole time.
Oh my god.
Okay, but yeah, basically, because I've been crazy, I got like 2 hours of sleep, not last night, but the night before, because I had to visit Fermilab, which is like the national, I had to get up early because I was visiting Fermilab, which is like the national like accelerator for like particle accelerators in the US, in Illinois, and that was super fun and awesome, but I got like no sleep because I had to get up really early for that and had to stay up late for nonsense.
Yeah.
But the thing that happened is I was like, you know, I did exactly what the way a normal person would react to that kind of situation, which is, actually, let's do 2 experiments instead of just 1. And so I had to go get the stuff. Somehow free overnight shipping was a thing. I can only bless the gods of Amazon and Jeff Bezos for that. But the package arrived early in this morning. I go to the package center just now because they don't open until noon Central, which is, I don't know, some other time Pacific. I don't know. It's all Eastern. It's whatever. They're just like, it's not here. You go look for it. They can't find it.
What?
And they're like going through all the bins. I'm just like standing there awkwardly, like I should really be talking to my chat or something.
Oh god.
And then I'm like, just walk out. Right as I'm walking out, the walk of shame. There it is. It's just lying on the outside.
Oh no!
It outside the door. The person, because the delivery person didn't deliver it to the proper place. That's why they couldn't find it. It was just sitting outside the door.
Oh god.
So thank God I went out that door. I don't even know why. Normally I don't know why I went out the back door, but I'm glad I did. So now I finally have the package of stuff. I have gloves. I cannot hurt myself.
Woohoo!
Well, I still might hurt myself.
Oh my god.
Oh my
that's
god.
Crazy.
So yeah, that's your update.
Dang,
yay.
Yeah.
Hopefully the arms are okay with my giant pipe cutter that has a huge blade on it.
Well, you're here, and we're live. I am here. Yeah.
We are live. Let's set up the. Do you have the, presentation up?
Yes, I have the presentation up already. Also, first off, nice. Chat, congratulate Xenotime for visiting Fermilab, and you also have a special announcement as well, right?
Do I have a special announcement?
About... Oh, I thought you wanted to share some photos.
Oh, I do want to share some photos, but we're doing that at the end instead of the beginning because I don't have time.
Oh, okay. All right, sounds good.
I was busy fighting the package people.
Yeah, the package center. You fought them off.
Exactly.
Yeah. So
I need to email them to tell them to stop looking for it because they're still looking for it.
Yeah. So chat, we're gonna be able to get some first-hand photos of Fermilab, which is crazy. I know some people work there, but I've actually never been there myself. So this is actually going to be really cool.
It's really cool. The whole like place is like a nature, very like open nature area.
Ooh, that's so cool.
They had like this huge area of land, and they were like, well, we'll use the parts that we need for the physics stuff, and then the rest of it we'll just like keep as like a wildlife preserve. So it's really cool.
Wait, that's so beautiful. I feel like it's good to touch grass every once in a while.
Yes, it definitely is. Let me...
Well, in the meantime, I wouldn't mind just getting started. I think my slides are first, so while you're getting started, I could just briefly explain.
Yep, I got your slides right up here. Or I will once I can reorder, once I can figure out how... There we go. Okay.
Yeah. And before we get started, really quickly, if you haven't already, go subscribe to Xenotime. He actually, you started like not too long ago.
Subscribe to Z.
Yeah, and he does chemistry, physics content, and a lot of really cool experiments, which is really impressive. So the Xenotime's POV is pinned to the channel, the chat. So just click the link there and click the subscribe button. And without much further ado, let's just get started. So, first off, really basic question. What is a star? What? Oh my god.
Oh no. Save me, Z. I don't know. I somehow ended up doing this collab without knowing what a star is.
Well, I think it's really important to understand, like, what a star is, because when people think of stars, they think, well, the sun or little dots in the sky. And I'm sure many of you guys also think of like a glowing ball of gas, and that's basically what a star is. A star is a massive luminous sphere of gas made of mostly hydrogen. And it's actually so massive that its own gravity compresses it, so that at its center there are these fusion reactions taking place. It's so hot that it's able to fuse atoms together. And the star is powered by this concept of fusion. The core at the center is like 10 million degrees Kelvin, if I recall correctly. And so the hydrogen slams together and forms heavier elements like helium. And that's what powers a star. But first, how do stars form? Where did these giant behemoths come from? Well, stars begin to form in these cold, dense molecular clouds, like this beautiful image here from NASA. And what happens is that this gas starts to become gravitationally attracted to one another, and they clump together to form protostars, which is a very fancy word of just saying a baby star. So this graph here on the left, I actually found it while just reading through some papers the other day. And it is a close-up view of a collapsing star-forming region. So that is literally a gas cloud, and at the center, that red area is collapsing to form a star. So the cloud is collapsing under gravity, and the magnetic fields, which are those little red dashed lines, are forming this hourglass shape. And at its center is forming these baby stars. So the formation of stars has to do with gravity, has to do with magnetic fields. It's a lot of different aspects together, but altogether it helps form these baby stars in these little stellar nurseries, which is, I think, a really cute way of explaining these clouds. So this is NGC 133IRAS4A, really fancy name. But basically it's forming a star. And we have been able to track that at the local, like, magnetic field level, which is crazy. So, you might be wondering, why is this important, Z? Like, stars are really cool, I love looking at stars, but, you know, like, why does it matter when stars are born? Well, the thing about stars is that they are pivotal for forming basically every single element in the universe. The only primordial elements, so at the start of the Big Bang, when the universe first started, were hydrogen and helium, Which makes you wonder, the rest of the periodic table is pretty darn big. So where did those other elements come from? And the rest of these elements, well, I guess maybe other than lithium and beryllium, because yeah, there's some trace lithium from the universe.
We're gonna get into that.
Yeah, and some lithium, beryllium were actually from cosmic rays, and there's also some like synthetic elements, but that's besides the point. Most of the elements must have been from a star. That includes like carbon, oxygen, iron, maybe even larger than that, like, I don't even know, like iodine. Because they weren't primordial, they weren't there at the beginning of the universe. So understanding stars, their death, their formation, is how we can help trace this story of matter. And what's really important is this concept of fusion. Fusion is not only important for understanding how the elements formed, but it's actually important for keeping stars alive. So what's going on inside of this star is this incredible battle between pressure and gravity. Tasty beryllium. No, don't eat beryllium.
Don't eat beryllium.
Don't eat beryllium.
You had to pick like the worst one too. For those of you who don't know, beryllium is like just beryllium in its like metallic form, just as the element, actually isn't like that toxic in general, except there's a chance that it's basically impossible to tell ahead of time. But there's a chance some people have like a genetic sort of thing where if like in contact with like the tiniest amounts of beryllium, like a speck of dust inside like laundry machine sized volume of air, then it will like can immediately like ruin your lungs and destroy you. Beryllium's terrifying.
Yeah, so TLD, beryllium baloney chat. No, we're not here to spread toxic information.
Don't let chat run a cooking show.
Yeah, no. We're not doing cooking. Well, we will be cooking later.
We're cooking with our slides. We're not cooking with beryllium.
Yes. Yeah, it may have the word berry in it, but it's not. Well, no, beryllium, No, there's no two R's. It only has one, but...
Minor update. I shot a half broken apart lithium battery across the room, so let's hope I don't explode it.
Oh my god, please be careful.
To give you a hint of which element we're going to be doing an experiment with.
I'm scared that you're playing with lithium batteries, but chat, please be cautious.
It's all right.
Yeah.
No, like seriously, like you have to know what you're doing, and don't just do silly things without knowing what you're doing. But if you do know what you're doing, then you can reasonably safely do silly things.
Yes.
I have gloves. It's fine. Gloves protect you from everything.
Yeah, but chat, we are not licking lithium either. Hello, Carbon, by the way.
I mean...
Alright, well, to continue with the slides, there is a basically ongoing battle between pressure and gravity inside of a star. Gravity compresses the gas inwards, and fusion pushes back outward with pressure because of the energy that's being produced. And this balance is also known as hydrostatic equilibrium, which is a very fancy way of explaining this. That balance is what keeps a star stable, and a star shines because a fusion is basically happening in its core nonstop. And if it were to stop, the star would collapse in on itself and then explode because it would just be incredible explosion. Not fun. So this diagram here on the right, Xenotime's going to go a little bit more about it in a second. It's also known as the...
I will once I fix the animation, because this is unholy levels of scuff.
It's okay. The X and Z in Xenotime stand for scuff.
I think every letter in Xenotime stands for scuff.
The X, the E, the X.
It's like the thing where it's like, because in English, like basically every letter can be pronounced a bajillion different ways.
Yeah.
Every letter in Xenotime stands for scuff.
This reminds me of that one meme where like all the letters are like written vertically, and wait, I think I can literally make this with I'll do it when you're talking, but we can make that later. But yeah, okay. We'll explain a little bit more about that. Actually, I think in the next slide. But the idea is one of the primary fusion reactions that's happening, especially in the sun, is the PP chain. which is a really funny name. It stands for proton-proton chain. I actually have your slides up right now, Xenotime, if you want to go ahead and explain that. So long as the scuff yeah, as long as the scuff is here and not at Fermi, we are good.
Yes, yes. Well, we'll have to make sure I didn't leave any, like, traces of residual scuff. I'm imagining, like, they have this, like, super cool looking control room that looks exactly like, you know, every, like, you know, like a Space Center control room. It's, like just a, you know, dimly lit room with a bajillion graphs and, like, blinking lights. I imagine they have, like, a scuff alarm that's going off as soon as I enter the campus.
It's like, honestly, if I ever get a chance to visit Fermilab and I just, like, walk in and it's like, wee, I'll know who it is.
Yeah, yeah. It's the radiation alarms are going off because I forgot I had a bunch of sources in my backpack.
Yeah. Should I just do scuff?
Do you want to share it over Discord, or I can put it in the slides? Either way.
Wait, I have your slides shared already.
Yeah. So I just need to go.
Yeah, just let me know when you're on the next slide.
We need to keep talking about scuff while I go download the video file.
Oh god. It's okay.
Wait, this was... oh my god. The original plan for this was for me to be able to, like, advance the animation, like, manually, like, one step at a time, so I could match it up with my talking. But since the, like, virtual camera thing makes my computer go really slow. Shout out Z, by the way. Z was like, don't do the virtual camera thing. We don't know whether it'll work or not.
That was a good call.
It didn't work.
I've added this little, like, thing.
Sorry, Ubuntu has experienced an internal error. Oh no.
Oh god.
Can I not upload files to Google Drive? I can do everything else on my computer except upload files to Google Drive? Okay, there we go.
I've added a little text box in front of your little reactive that's, like, spelling on Xenotime, but, like, it ends with scuff. Yeah.
I am the Scuff Lord.
Yes. Scuff Lord.
Move over, Doctor Who. Who needs a Time Lord when you have a Scuff Lord? And I uploaded it to the wrong Google Drive account.
Oh no! It's okay.
Okay.
I think this
so
genuinely
bad.
might be the most scuffed stream on my channel.
Oh no, totally. And we haven't even tried to do the thing. I haven't even tried to cut up lithium batteries yet.
Oh no. Wait, I do. Oh, I can, like, share your little hand cam too.
It's up.
It's up. Okay, so
allow anyone to link with access. Yes. Okay, there should be a video.
should I refresh the slides?
I spent way too long on this.
Wait, should I refresh the
So
slides?
I have to. Oh, maybe.
Yeah, I'll do that real quick.
I'll see if it shows up on mine.
Here, I'll just quickly refresh. Oh yeah, I do see the video now. Here, let's just move it.
Okay.
Slides. Okay, there we go. Okay. All right. It's time for PP chain. Let me click the next. Okay, I'll play
That
the
slide
video.
was always there. All right.
All right.
But
let's see this.
yeah, so the idea is you merge two protons together, and then what happens is that one of them turns into a neutron, and then when you make two of those, they can slam together and make then, like, the regular isotope of helium. Now, helium-4, what's the big deal about making helium-4? Why do we care so much about making helium-4? We care about helium-4 because it's what's called an alpha particle, and generally alpha particles will, like, get involved in nuclear reactions. So, like, if you watch the, like, antimatter, the stream making antimatter I did, that relied on the fact that some nuclei, you can shoot alpha particles at them and they'll just, like, gobble them up. But a similar thing happens in stars where, like, the reason that this stage of the PP chain is so important is because alpha particles can then react with other nuclei to form not super big nuclei, but, like, we're talking, like, they can form, like, carbon, if you basically just get 3 of them to smash together really fast. And they can form lithium and other, like, nuclei that are you know, above hydrogen and helium, but not, like, the super big nuclei. You have to do other shenanigans for that.
This is a really great animation, by the way. Did you make it in Manim?
I did make it in Manim. It probably was not worth the time I spent on it, but I'm glad you think it's good.
Looks great, though. And this is a really great demonstration instead of a really complicated looking diagram.
Yeah, like, I feel like the graph is just, like, or the graphic is just, like, scary.
Yeah.
but it's not that bad. You just hit the things, and then the other thing to sort of notice that's handy is when we get to like when you stick two protons together, what you have is a nucleus that it's very like unbalanced. It's almost entirely like protons, and generally an unbalanced nuclei will protons will turn into neutrons and vice versa. They'll transform in order to like get closer to like being more balanced. Right, so that's a pattern that you'll see happen a lot, and it'll come up later. Is you'll make like unbalanced nuclei, and then they'll radioactively decay by changing between protons and neutrons.
Mm. Yeah. All
right, we can continue. You can see that so far we've made helium, we've made hydrogen. There are still a lot more elements for us to make. So let's talk about lithium. Let's talk about how we make lithium. I know the Z mentioned it a little bit, but some lithium was actually produced not in stars, through various like complicated cosmic ray processes. But some of it is. There's a certain kind of star that does this better than other ones, which is called T-Tauri stars, which I have a cool picture of. But then basically we can just like continue this like this whole proton chain thing. So we made helium-3, we were able to smash them to get helium-4. So we have helium-3 and helium-4. If those smash together, then we get this like 7b, which is beryllium, and that's a like unstable nucleus. It will one of the protons will switch to being a neutron. There we go. One of the protons will switch to being a neutron, and we'll get our delicious lithium. The problem, the thing here is that lithium-7 ends up getting involved in other reactions. So stars make lithium. They make lots and lots of lithium. The thing is they use up the lithium like almost as soon as they make it. So maybe some of the lithium comes from this. I don't know. This is actually hint. Like we still don't know where all of the lithium comes from. It's kind of like an unsolved problem. But then in 2020, this paper came out where they were like, actually, stars make heaps of lithium, but through supernova. So when stars explode, they'll like shoot basically just globs of whatever stuff they're working on, and when you shoot it out, the pressure is just down and everything. Fusion just like basically stops in its tracks. And so if you're like the star's in the process and it's making some lithium, and it's making lithium, but it consumes it immediately. If it like shoots out a bunch of its like work in progress nuclei, then there'll be some lithium in there. And apparently like 10%-ish vaguely of, according to this paper, like 10%-ish of nuclei comes from this like ejecta from supernova. There's a specific type of supernova that's simulated, which this paper very confused me, and I still don't totally understand everything, even though I work with like these kinds of simulations sometimes. So maybe that's means that I'm not very good at it. But
well, I didn't get a chance.
Really cool paper.
I didn't get a chance to read it in full just because I saw the paper like 30 minutes before the stream started, but I did skim the abstract, and what I got from it was like basically what they did in the simulation. So they use a simulation known as NOVA, which is a 1D hydrodynamic code. It's like a fancy way of saying it's like a special type simulation. Yep. They simulated these stars with solar material, and then they simulated this thing called a thermonuclear runaway event, which is what happens at the surface of white dwarfs. Basically, things get so hot that it starts to gain material, and this layer of material keeps like exploding. It's very active. And they switched between like white dwarf and solar material within the stars. And yeah, like you said, what they found was that these stars eject gas that is very rich in beryllium, and that material then decays to form lithium. And they concluded
exactly
from what I read from skimming this paper is that these carbon oxygen novae contribute to a lot of the lithium that is in the universe. And what's more spectacular is that they noticed that the white dwarf is actually keeping more material than it loses. And that's important because a primary thing about white dwarfs is that they create type 1a supernovae. So that's why the title says, as well as potential supernova 1a progenitors. Progenitors is a fancy way of like saying like causers or whatever. So they're saying that
like producers almost.
Yeah, so it produces lithium, so it answers this question of how lithium is formed, and it actually builds up the white dwarfs so that they can lead to type 1a supernova, which is a special category supernova that has to do with white dwarfs. So I thought this paper was really cool. I'm going to read it more detail after the stream, but I also put it into the chat as well if you want to take a closer look.
Yeah.
Yeah.
If you what?
If you want to take a closer look, I put the link into the chat as well for those of you who are on my stream.
Yeah. Nice. Yeah. You can see the DUI in the corner if you really want to.
Yeah.
It's a good read though, although it definitely left me confused at some point. Especially because one of the things, like, sometimes science writing just does stuff like this, where they say CNE to refer to, like, they use the acronym C and, like, lowercase e to refer to, like, CN ejecta, but then they never acronym is. So I spent forever thinking they were saying, like, carbon neon.
Oh no!
It was, like, really confused.
Yeah. Yeah, but this is a cool paper.
Yeah. All right. Anyways, it is a really cool paper. Yay.
Oh my god, why is there an iron pipe sound on every single slide? Well, okay. So fusion stops at iron because
Zia's here to educate. I'm here to make the stream entertaining by being a menace.
Oh my god. So fusion stops at iron because fusing iron doesn't release energy. So if you see this little onion diagram here, I love this diagram because it shows that after fusing basically every single element, what's left is an inert iron core, which means that fusion doesn't produce any energy.
Or fusion even, like, loses energy.
Yeah.
It can still happen.
Yeah.
That's a pressure vessel. That's a bomb. Let's not make bombs by accident.
Well, oh my god. And so this explosion here, speaking of bombs, is V838 monocerotis. So it was.
You're welcome for that slick transition.
Yeah. So it was observed in early 2002 as experiencing a major outburst. So yeah, the star explodes. I love this animation because this image actually took many years to create, and you can actually see the layers exploding like that. So you might be wondering, wow, we made it to iron now. So how do we cook elements heavier than iron? Well, if you can see here, there are some heavy stars and neutron stars in this cooking jar with cooking Z. So,
oh fuck.
There's this fancy process known as R process. It stands for rapid neutron capture, so you can see it here in the R. This occurs in neutron star mergers or at the center of supernovae, so incredibly high energy, high density environments. What happens is that the neutrons are captured, as you can see. I think if I move my mouse here, maybe I have like the laser pointer. Turn on laser pointer. Yeah. If you can see here, the neutrons are being captured very quickly, faster than a nucleus can decay. So this actually pushes the nuclei far from stability into these neutron-rich isotopes, and then they decay back towards stability. And what this does is, if you can see here, what's happening is we're able to create heavier and heavier elements, including gold, platinum, uranium, so some of the heaviest and most stable isotopes ever. So these neutron captures happen very quickly, so they can reach very high neutron numbers and then decay into stable elements. There's also another process here known as S process. And that, very surprisingly enough, is standing for slow neutron capture process. So this happens in less dense environments inside these stars called asymptotic giant branch stars, these big red stars. And neutrons are captured slowly compared to the R process. And so they build these elements sort of step by step. So that's this like light blue line here. It sort of goes up here, sort of building them step by step. And it creates these heavier, stable nuclei. And these are responsible for creating the elements in the middle of the periodic table, like strontium, barium, and lead. So the difference between the S process and the R process is that the S process is slow, and the R process is rapid. And then there's these other ones, VP process, RP process, which rely on like gamma ray bursts and so forth. Honestly, this could be a whole other stream of itself, but I wanted to bring attention.
There's like, yeah, there's a ton of different ways. So like the S and R processes are for like capturing additional neutrons, which is generally like a pretty common thing. Just like, this is just a quirk of nuclear physics. Like nuclei are generally pretty amenable to like you shoot neutrons at them, they absorb neutrons. With protons, it's much rarer, and so there's all kinds of totally bizarre ways to make like proton-rich nuclei. They're called p nuclei, and that's why there's like so many crazy different processes here.
Yes, physicist naming conventions, very fancy. Yeah, and
Yeah.
this is the second to last slide before the second experiment, which I think is perfect timing because we only have like 15 minutes left. So
Yeah.
this is a diagram showing I love this diagram. You can go to it, the link down here. It's just a Wikipedia page if you look up nucleosynthesis. You can see where all the elements came from. So hydrogen and helium came from the Big Bang. Lithium came from cosmic rays, also a little bit from the Big Bang. And you can also see the rough ratios of where these other elements are being created. There's also these diagrams that are incredibly precise with these. This is like a pretty like generic diagram. There's ones where they actually have the exact ratios down for each of these elements and where they came from. So isn't that chart outdated? Thought a decent chunk of heavier from neutron star mergers. Yeah, I think they actually just classified that under
chart gets
supernova.
updated constantly.
Yeah.
Sorry, I interrupted you.
I think they just classified that under supernovae in this case. That was why I was saying there are diagrams that are a little bit more precise than this, but I just wanted to show this one really quickly. Yeah. So. All right. Experiment number 2. Let's get started.
Okay. First of all, we have to go back to your chart of all of the different processes.
Yeah.
Because this is something you'll just have to trust me on. But there's certain nuclei, like these processes can only make certain nuclei, right? So it's the SNR process to create neutron-rich nuclei that are neutron-rich, and then they can decay, blah, blah, blah. If you want to create proton-rich nuclei, we have the RP process, the nu-P process, the P process.
Yeah.
None of these can produce the isotope lanthanum-138. There's no way for any of these processes to produce the proton-rich nucleus lanthanum-138, which if you put the hand cam, I guess I can write it out. And I need to put that too. No one can make lanthanum-138. There cannot be lanthanum-138. You cannot have lanthanum-138. And my image is blocking it. Let's move that. And there we go. Yeah, no one can have lanthanum-138. So let's go ahead and just check. Let's go check. Let's go check, see if is there any lanthanum-138 here? I don't know. Let's find out. Because it turns out, and this is actually amazing, at Home Depot, you can buy this pool for phosphate remover, which is lanthanum chloride. I don't even need to wear gloves for this part. It's not like the lithium stuff. Yeah, so this is the chemical lanthanum chloride, which is soluble in water. It's chemistry stuff. It will like complex with phosphates and make them insoluble in water, so it'll like fall out and then there's less phosphates and floating around in your pool. I don't care about that. I care that it's made with this super weird element lanthanum, and there should not be any lanthanum-138. None of the processes we've talked about can produce all of these processes. None of them can produce lanthanum-138. So let's I swear, last time I spent there we go. I've learned. I can open this up now. So let's Oh, the other thing, I don't have a picture of this. We'll get to that. We'll get to why I'm doing this whole thing in icy cups. Not sponsored. We'll get to that in a second.
Mm-hmm.
But what we're gonna do, the basic reaction that we're gonna do.
Chat is suggesting you use gloves, by the way.
Yeah, I will. But my point is, it's not like that dangerous. But anyway, the reaction we want to do is we have lanthanum chloride. And I have sodium carbonate, which you can buy just as like laundry stuff. Shout out random household chemicals. Then you can mix that with sodium carbonate, and you'll get just like a switcheroo where they switch places, and now you get lanthanum carbonate and sodium chloride. Now sodium chloride is just table salt, right? So that's soluble in water. That'll stay in water. Lanthanum carbonate is the only thing in this equation that's insoluble in water. So it'll like come out of solution and it'll look like a white precipitate. This is very handy. It's actually lithium chloride that we were using the fact that lithium carbonate is insoluble in water. Most carbonates are soluble in water. This is weird. Lanthanum and lithium are weird. Maybe it's because they both start with L. But anyway, what we can do is use this to like extract the lanthanum from our pool chemicals. So let's mix up some sodium carbonate.
Oh my god.
In this icy cup. So we just get some water. We'll need to, because sodium, we'll need to make everything else, dissolve in water, right? So we'll get some of this. I can put gloves on. Gloves are good. We like gloves. Yay, gloves.
Everyone's shocked by the icy cups. Well, this is very scary, but you should wear gloves. Probably.
Okay, this is the lithium thing is the lithium thing is genuinely scary. This is not scary. I mean, okay, at least by my standards. Maybe my standards are kind of messed up. Anyway, let's make up our sodium carbonate solution. We just need enough where it doesn't really matter how much, because again, this is a very convenient reaction because the only part of this reaction that doesn't dissolve in water is like our product. So we don't have to worry about like using too much of something, because as long as it all dissolves, then we're good. And in true icy fashion, I have the icy straw to stir it with.
Oh my god.
Yeah, so we're just making up our solution of sodium carbonate because yay, chemistry. And I guess while we're doing this, I can explain the reason it's in icy cups. Is the first time I tried to do it in just in normal cups, but they were all out. I normally steal them from this like convenience store place at our university. But they were all out of normal cups. So I asked if I could use the icy cups and they were like, okay. And basically the reason this had live-ish thing is that actually like analyzing, so we'll do like the synthesis part here, we'll make the chemical. Actually analyzing the chemical was like I had to do at the university, like using their equipment it took like 4 hours. It was a pain. But so we'll make the thing and then we'll just like fast forward and use the analysis results from when I did this before. But reproducibility and all that, right? I did it in icy cups the first time. If we want these analysis results to be comparable, we want to be properly scientifically reproducible. I got to do it in icy cups this time too. But that dissolve? That seems mostly dissolve. The like silly thing about this is it's not like I work in a lab and just like walked in to go use this like mysterious piece of equipment and I haven't explained what it is yet. We're using it for like a class, for our like physics lab class. Let's add a little bit more. So there's like, they're doing makeup labs because it's like almost the last week of school. And, I don't have to make up a lab. So what I do instead, because of course I do, is I imagine you're the TA and it's like halfway through the makeup lab period. There's like one other person who has to make up their lab that you're just like waiting for them. And this random kid comes up with an icy cup and says, can I put this in the gamma spectrometer? That's the secret piece of equipment. It's equipment that measures the intensity of gamma rays, the energy of gamma rays emitted by like a substance. Which now implies that the thing in the icy cup is radioactive.
Oh my god.
Imagine you're the TA. And this is like, hey, can I with this like icy cup full of stuff. But I did. The TA was like, how radioactive is it? And I was like, it's not actually radioactive. What we're trying to do here, the thing about lanthanum-138 is lanthanum-138 is very slightly radioactive. There's a it has, if we were, the way we're going to detect it, because we can't do the thing that I was trying to do with the lithium with mass, because, 138, 139 are so close to each other. But what we can do is, since lanthanum-138 is very, very slightly reactive, it has a half-life of like 10 to the 10 years or something, we could maybe detect the gamma rays that it emits. So, anyway, this looks like we almost have our sodium carbonate solution. But yeah, so that's the idea. We'll get a gamma spectrum of lanthanum-138. And then, once we get that gamma spectrum, we can look for a peak at the energy of this thing.
Oh my god.
So that seems mostly dissolved. But of course, in order to do that, we have to, this solution, as you get it from the hardware store, it's mostly almost entirely water. And it's just water. Right? So we got to extract the lanthanum. That's what we're doing. We got to extract the lanthanum. And this also is a nice way of confirming that it's lanthanum, because again, not many substances form insoluble carbonates. Okay, there we go.
Chat is asking, what's its decay method? I guess it's just...
it actually can decay two different ways, and one of them is very weird. It can decay by beta minus decay, which is the normal thing where it like, ejects an electron and proton turns into a neutron, I think. So that's like the normal typical way. It can also decay by double electron capture, which is super weird, which is when it like two of the electrons in the atom get like, react with the nuclei. Nuclear physics is weird. And it turns out that this is like kind of, but not the same thing as beta minus decay, because like a positron is an antimatter electron. So the way it works out is you can either like, there's the two decay modes. You can either emit an antimatter electron or absorb a normal electron. And they kind of behave, more or less similarly. So I'll add a little bit more water. Did I loot this just because? We gotta make sure everything here is
I will
dissolved.
need to leave in like 8 minutes. For context, for those of you who
Yeah,
joined
okay.
late. Yeah.
We're really close.
Yeah.
All right, so now we add in our. Oops, we add in our delicious lanthanum chloride.
Oh my god. Oh my god. Oh my god.
And this isn't maybe super easy to see on camera, but there's this white junk on top.
Wait. You should bring it a little closer to the camera for a split second to
I will.
show.
I want to put the lid on first though, so I don't like trip on it or something. Safety first.
Ooh, what
Look
is
at
that?
Those white crystals are lanthanum carbonate. That's our product.
Huh.
So now we can get another icy cup and filter it off into that. And
This was not that as scary as you trying to cut open a battery.
No, it's definitely, again, this is chill. The battery thing was kind of unhinged. But I thought in the worst case, even if it fails, it'll be kind of entertaining.
Yeah. Why does it also kind of look like icy?
It does. I didn't even notice that before.
You should make sure to throw it out so that no one's accidentally. Yeah.
Yeah. The other cup I actually did label. But what happened is, I'm on the way. Oh wow, that's I made like way more of it this time. Wait, there's our delicious.
Oh, yummy!
Delicious pure product. And the question, of course, is does this have lanthanum does this have lanthanum 138? Because there's no process that we've none of the processes we've talked about should be able to make lanthanum 138. So I'll just leave this to go, and I will take off my gloves as we let this do this. And I can put them in the toxic corner. All right. Let me briefly. Yeah, so lanthanum 138 can't be produced by any of these methods. I talked about that. We'll let it filter. I made way more than I did last time, I guess. I don't really know why. I think last time I used way less sodium carbonate because I was nervous about it, like co-precipitating. Which is there's weird effects sometimes when you're like precipitating something. Sometimes it will drag other elements with it as it crystallizes. It's a very weird effect, but it's actually a very useful effect for doing this kind of thing. Because when you're not doing this, when you're working with like actual radiochemical isotopes, you often have such a tiny amount, like maybe 500 atoms of one substance, and so it's not something you can work with like in bulk. No one can see or handle like 500 atoms. So co-precipitation is actually very useful for radiochemistry because you can have some bulk thing, and if that will co-precipitate your radioactive whatever you're trying to work with. Now you have like a bulk solid that contains the thing you're trying to isolate, even though it's maybe like 500 atoms or a very, very small amount of actual substance. But let me go find the gamma spectrum that I had.
This is really cool.
Which I thought yeah, this is actually reasonably safe and stuff. Again, there was the other thing was a bit unhinged. But yeah, so these as they dry, you'll see they're just like white crystals. The other ones were maybe a little bit more crystalline.
Yeah, I'm hoping that we can show the gamma thing because. FYI, I have like a very important meeting like at 12 and it takes me like 20 minutes to get there. So
yeah. I will. I'm rushing to find it. Okay, let's turn off.
I also wouldn't mind if you want to share photos from your from Fermilab.
I'm sending one Fermilab photo and one gamma spectrum photo.
Oh. Okay. I was okay. Yeah. Let me just quickly download those.
See, the other one is a video. I don't know why I took a video because it's just a graph on Excel, but
yeah. Let me quickly show the Fermilab photo first. Wow, this is cool, by the way. Oh, it's huge.
Thanks.
Let me make this a little smaller.
Yeah, it really is.
Ooh, well, it's a little cloudy, but it looks great. This building is very hyperbolic.
It's really cool. It's a really cool building. Copy image link. Okay, let me cheat and put it where the slides were.
Sorry for the scuff. Yeah, and for those of you who are heading out, thank you so much for joining. So sorry for all the scuff. It was
That's me. Don't blame Z, blame me. I brought all of the scuff.
And let me add the video real quick. Here.
Yeah.
Oh,
Let me
whoa.
make sure my chat can.
What is this
Hopefully
showing?
you guys can see that. Okay. So let's talk about that. Let's talk about that gamma spectrum. What's up with that? What's up with that? What's up with that gamma spectrum? Okay. So this is the spectrum of like gamma energies or whatever, like the energy of the gamma rays that are emitted by this isotope, and it looks like complete noise. This is the worst gamma spectrum ever taken by any human in the history of existence, probably because it's, you know, on some sample I made with Home Depot chemicals, and I just like cobbled a bunch of lead shielding I found around the room around it. But if you look at it's like between 859 and 872. There's a very, very slight peak. There's the world's tiniest, cutest little peak. And between 859 and 872. And that peak corresponds to within 0.2% of the actual gamma ray energy of lanthanum-138. Somehow, with this awful gamma spectrum, like shielding from just around the room and like Home Depot chemicals and icy cups, I managed to get a measure. Not only did I detect lanthanum-138, I measured its energy to within like 0.2% of the accepted value. Science is awesome.
That's crazy. Also, I love how this is a video.
Yeah, you can pause it or something.
Yeah,
it's the one that kind of looks like the DC Capitol building or something. But yeah, it's in between 859 and 872.
Oh, right there.
And yeah, it's the cutest little peak. Because when I first did it, I basically had to spend like I spent like 2 hours getting data and then like 2 hours like doing corrections. But with all of the corrections, I got within really, really close to the actual value. And so how does this work? How does lanthanum-138 get made? I thought it couldn't get made. It gets made by neutrinos. In supernova, there's so many neutrinos that even though most there's like trillions of neutrinos passing through your hand every second, you know, they go straight through Earth, they don't do anything, they don't interact with anything. Yet in supernova, there's like 10 to the 58 neutrinos or something. There's so many neutrinos that they can actually alter matter. And in this case, that's what's happening. That's how lanthanum-138 is made. It's called the new process. It's made by like these particles that almost normally, you know, there's literally like insane amounts of them going through Earth just not doing anything. They can make, actually, there's so many of them in a star, they can make radioactive nuclei that can't be produced any other way.
Wow. No, this is so cool that you were able to measure this. Yeah, no, chat is also saying how exciting this is. This is cool.
I know, it's like, it's this insane thing. Like, it's the, you know, in a supernova, the fact that I can, you know, with my crappy Home Depot chemicals and begging the TA to use, you know, whatever like lab equipment we have from the 90s.
Wow.
That you can, yeah, and there's something about it where it's like the lanthanum was here all along, right? We're just observing it in the Home Depot chemical, right? You know, ages and ages ago, some stars had this like they exploded, and there were so many neutrinos, the particles that normally do absolutely nothing and pass through everything totally fine, were able to transmute nuclei, and the fruits of that process are just like sitting on a shelf at Home Depot.
Yeah.
They're just there.
Yeah, well, this is really cool that you got a result like that.
Yeah.
I do have to say,
you have to leave now, though.
Yeah, I really have to run, but we should run this back. I think, chat, if you guys have any ideas, feel free to put in the Discord. Also, Xenotime's channel is linked in the pinned comment. Also, I was thinking...
Yeah, and go subscribe to Z.
Yeah, thank you so much. Also, I was thinking we could do an unofficial raid. A bug teacher streamer of mine is actually streaming at the same time, so let me just like type this up real quick. I just need to paste this.
If you paste it in Discord, I'll put it in my chat too.
Yeah.
I know you have to go. That's not.
Yeah. I'll have to run right
Thank
now.
You so much.
But if you guys want to raid, do a cross-platform raid to Entomolomoth, who does bug content, that would be really cool. I really want to support other like science VTubers, and I thought that would be a really great way to close out the stream. Anywho, I'm just gonna type in Z-raid.
All right, you gotta go now though. So thank you so much.
Oh, they're also live on YouTube. Wait, actually, oh my God, wait.
You guys can find them. I trust you guys.
Yeah.
I believe.
Either
I believe
on
in
Twitch or
chat.
YouTube. All right. Okay, I gotta go. Really important meeting.
Bye, bye,
But
bye.
Thank you so much. Bye.
Bye. This was so much chaos. It's fun. Bye.
Bye.